Hello again. Let's try out some exercises in kinematics. Why don't you grab a pen and paper? Feel free to pause the video whenever you need to. Let's start out with some concept review. Can you remember what these variables mean? What about x? If you said position, that's right. How about v? What does v stand for? That's right, velocity. How about our last variable, a? If you said acceleration, you're right. Okay, let's move on. Do you remember the equations for velocity and acceleration? Velocity is the change in position over the change in time, whereas acceleration is the change in velocity over the change in time. How about some math? Let's say we've got a T-Rex at position 2. Then he wanders along down to position 10. This journey takes him a total of 4 seconds. Can you calculate his velocity? Why don't you pause the video and think about it? Alright, how about we walk through it together? Let's first calculate his change in position. His initial position, 10, minus his final position, 2, is 8. Since velocity is his change in position over his change in time, we can calculate this by dividing his change in position, 8, by the change in time, 4 seconds. Thus, his velocity is 2 units per second. Let's say these units are meters. This is a typical SI unit for distance. Then his velocity is 2 meters per second. Let's try something a little bit different. Here I'll give you a velocity, 50 meters per second to the left. Can you calculate the distance traveled? Alright, let's see here. Our Ferrari is traveling at 50 meters per second for 10 seconds, and we know that velocity is the change in distance, the change in position over the change in time. Then we can solve for change in position by multiplying the velocity times the change in time. So we've got delta x equal to 50 meters per second times 10 seconds. Our seconds cancel out and we end up with 500 meters. Let's do some work with acceleration. Our T-Rex is jogging along at 4 meters per second. Then he accelerates for 5 seconds, and then after this time he's running at 24 meters per second. That's pretty quick. Can you calculate his acceleration during these 5 seconds? Let's give it a shot together. Acceleration is the change in velocity over the change in time. We know that his change in velocity is his final velocity, 24, minus his initial velocity, 4. This we divide by the change in time, 5 seconds. We know that these are in meters per second. Then we end up with 20 over 5 meters per second squared, which is 4 meters per second squared. Awesome. Let's work with an acceleration in a slightly different way. Here I'll give you an acceleration 4 meters per second, at which our Ferrari is moving. Let's say our car undergoes this acceleration for 10 seconds. If it starts at rest, 0 meters per second, what is its final velocity? Alright, even though this problem looks a little bit different, it's still simple. We know that acceleration is equal to the change in velocity over the change in time. We can rearrange this to state that the change in velocity is equal to the acceleration times the change in time, which is 4 meters per second squared times 10 seconds. This leaves us with a speed of 40 meters per second. Perfect. How about one last problem? In this one, our T-Rex has an initial velocity of 2 meters per second. He then accelerates for 10 seconds at 3 meters per second squared. Can you find his final velocity? Let's see here. The change in velocity is equal to the acceleration times the change in time. So we have 3 meters per second squared times 10 seconds, which is 30 meters per second. But remember, this is only the change in velocity. It doesn't account for his initial velocity. We have to add his initial velocity to his change in velocity to find his final velocity. So 30 meters per second plus 2 meters per second is 32 meters per second. Great job!